All right, so up next is Tommi Muller from the University of Oxford, who will present some joint work with Nanda. And Tommi will talk about multilinear hyperquiver.
Okay, thank you for inviting me to speak. And you can find this paper on arXiv with the same title here. So first of all, what is a quiver? A quiver is just a directed graph. And a quiver representation is an assignment of vector spaces to the vertices of this graph and linear maps to the edges of the quiver. So concretely, you can have a quiver that looks like this. And here we put vector spaces C to the DI for each vertex I, and we have some matrices representing the maps that are put on the edges. So from a mathematical point of view, quivers are interesting for a lot of reasons. One is that you can use what's called the path algebra of the quiver to classify finite dimensional algebras up to something called Morita equivalence. And there's quite a lot of rich Lie theory that you can do with quiver representations. You can also use geometric invariant theory to construct moduli spaces of quiver representations, and these give you objects called quiver varieties. And another reason is if you have a variety X, there exists a quiver Q, so that the derived category of coherent sheaves on X is equivalent to the derived category of representations of Q. So quivers help you understand complicated coherent sheaves. But quivers also have a number of applications. They are ubiquitous in topological data analysis. You always run into them when you do persistent homology, and quivers are quite impossible to avoid here. In some work done by Harm Dirksen and Visuma Kam, quivers have been used to study matrix normal models, and these are matrix-valued generalizations of Gaussian distributions. And in work by Anna Seigal, Heather Harrington, and Vidit Nanda, there is an investigation on generalizations of principal component analysis, where the principal components lie in a span of an assignment of globally consistent choice of vectors on each vertices, like in some sense like a global section of the quiver representation. And this might be useful, for example, if your data has some linear relations that are satisfied internally. So quiver representations extend linear algebra in a lot of ways, and this is how we're going to approach them. So if you have a quiver Q with n vertices, we write for an edge E from vertex I to vertex J, its source vertex, S of E equals I, and its target vertex, T of E equals J. And let's say Q has a representation, which assigns the vector space C to the DI to every vertex I, and dj by di matrix AE for every edge E from I to J. Then if we have a tuple of vectors, one vector that's placed on every vertex, we call this tuple a singular vector tuple of the representation if for every edge, the linear map on that edge assigned to the vector on the source vertex is a scalar multiple of the vector on the target vertex. And we can think of these vectors up to scale, so we can think of them living in projective space. This allows us to draw some pictures for various kinds of eigenvalue problems. This quiver on the left here, which is called the Jordan quiver, its singular vectors are the vectors x such that ax equals lambda x. So these are just the eigenvectors of the matrix A. In the middle quiver, there's two vertices, so now you'll have two vectors x and y, and this pair xy, if it's a singular vector tuple of this representation, then it is a singular vector tuple of the matrix in A in the usual sense. And this quiver on the right here, this is what's called a Kronecker quiver, and its singular vectors are solutions to the generalized eigenvalue problem for the matrices A and B. So if we have such a setup, then it's very natural to just generalize this from graphs to hypergraphs and from linear to multilinear algebra. And we want to take these quiver pictures and turn them into something more complex, something that involves tensors and hypergraphs and so on. And these are the kinds of objects we'll be looking at, and we will call them hyperquiver representations. So let's just lay the rules for this game. A hyperquiver, H, is a set of vertices V of size n and a set of hyperedges E, such that for every hyperedge E, there's some positive integer, m of E, associated to that edge, and there's also an ordered tuple of vertices, V of E. So we call the jth entry of the tuple V of E as S sub j of E, and we will call the first m-1 vertices of this tuple the sources of E, and the last vertex in this tuple the target of E. So what this means is that in our quiver, hyperquivers, every hyperedge can have some number of input vertices, but always one outgoing vertex. And so now we can talk about representations of hyperquivers. If you have a hyperquiver H and some dimension vector D, it's some integers d1 to dn, n is the number of vertices, then a representation is an assignment of the vector space C to the di for every vertex I, and an assignment of a tensor Te to every hyperedge E of the correct dimensions, which we think of as a multilinear map, taking the vectors at the source vertices to the vector space at the target vertex. So we're contracting the tensor along the hyperedge. And so let me explain what these hyperedges are doing. So in the Jordan hyperquiver, on the very left, you have one vertex, so one vector x, and this just takes the x and passes it through the tensor T. In this picture, the red hyperedge has two incoming vertices and one outgoing vertex, so we'll need a tensor that's order 3. In the middle hyperquiver, 3 vertices, 3 vectors x, y, and z, and the different shades of green hyperedges will contract the tensor along different components, and these are the multilinear maps on the edges. And likewise for this Kronecker hyperquiver, where you have 2 hyperedges and the tensors, 2 tensors A and B. And so now that we have this set up, we can just say that a tuple of vectors x1 to xn is a singular vector tuple for a hyperquiver representation if for every hyperedge the contraction of the tensor on that edge with the source vertices is a scalar multiple of the target vertex. And we will denote the set of singular vector tuples of a representation R as S of R. So what's this saying now? So what are the singular vectors of the Jordan hyperquiver? These are just the eigenvectors of a tensor. what are the singular vectors of this middle hyperquiver? These are the singular vectors of the tensor in the usual sense of the word. And with the Kronecker hyperquiver, these are solutions to the generalized tensor eigenvalue problem. So S of R, the set of singular vector tuples of a representation, it's a subvariety of the product of projective spaces, one for each vertex. And explicitly, it's given by the vanishing of 2 by 2 minors of a collection of matrices, one matrix for every hyperedge, and it's the matrix where you have on one column the contracted tensor, and on the second column the target vector. And these are all variables because we want them to be parallel. So notice that in the case when the hyperquiver is a Jordan hyperquiver, this singular vector variety is a reduced version of the eigenscheme of a tensor that Hiro gave a talk about yesterday. So now that we have a variety, the very natural question to ask, of course, is what is the dimension and what is the degree of this singular vector variety? In this context, by degree, we mean the degree of its image under the Segre embedding. So in this talk, we're going to go through some examples of zero-dimensional singular vector varieties, just to make things simple. And so it'll consist of a finite number of points, singular vectors, and we want to know its degree. We want to know how many points are in the singular vector variety. So let's look at the Jordan hyperquiver, the eigenvectors of a tensor. So there's a theorem by Dustin Cartwright and Bernd Sturmfels, which says that if you have a generic tensor of dimension d and order m, the number of eigenvectors of T is m minus 1 to the d minus 1 over m minus 2, and each of these eigenvectors have multiplicity 1. So in this context, singular vector variety has dimension 0 and degree equal to the one given in this theorem. Now if we look at this quiver here, we're talking about the singular vectors of a tensor, one tensor. And there's a result by Schmill, Friedland, and Giorgio Ottaviani that if the tensor T is generic, then the number of singular vectors is equal to the coefficient of some particular monomial inside of this product of polynomials here. And again, the singular vectors occur with multiplicity 1. And one more example is, again by Friedland and Ottaviani, but also independently by Ding and Wei, that if A and B are a generic pair of tensors, dimension d and order m, then the number of solutions to the generalized tensor eigenvalue problem is d times m minus 1 to the d minus 1. And again, we have multiplicity 1 with each solution. So these are examples of dimension and degree of various hyperquivers. So if we, again, just to reiterate, if we want to generalize all of these results, what we have to do is to find the dimension and degree of the singular vector variety. The problem, however, is that all of these results refer to generic tensors. So we need to ask ourselves the question, what should the hyperquiver analog of a generic tensor be? How should one define a generic representation? And we have one answer, which I'll explain. So first I'll establish this firstly. So if E and E prime are edges in your hyperquiver, then two tensors TE and TE prime agree up to permutation if the corresponding tuples associated to the edges agree up to a permutation sigma, and sigma takes the entries of one tensor to the other. So two tensors agree up to permutation if they're secretly the same in disguise and they're just reshuffled versions of each other among the same vertices, which the two edges share. And now I'm going to try and define a generic hyperquiver representation. So let H be a hyperquiver, R be a representation. So firstly, we define the partition of R as the unique partition of hyperedges, E, such that for any two hyperedges within each piece of the partition, the tensors, the two tensors on those two edges agree up to permutation, and no two edges in each piece contract T along the same component. So if you have a hyperquiver representation, there will be such a unique partition. And once we have this partition, we say that the representation is generic if you look at the tensor in each piece of the partition. It's really the same because they agree up to permutation. And this tuple of tensors has to be a generic point in the product of tensor spaces. So this is our definition of generic. It includes the three hyperquivers we saw earlier as examples. And so now that we have this notion of generic, we can now state our main theorem. So the theorem says, let R be a hyperquiver representation that's generic, and let S of R be the singular vector variety of this representation. Let N be the sum of the projective dimensions of the spaces at each vertex minus the sum of the projective dimensions of the spaces at each target. And let D be the coefficient of this monomial inside this product of polynomials here. Now the product will depend on the edges and the vertices, like this. Then the singular vector variety is empty if and only if D equals 0. Otherwise, the singular vector variety has pure dimension n and has degree d. If the representation has finitely many singular vector tuples, meaning if the singular vector variety is zero-dimensional, then each singular vector occurs with multiplicity 1. So this is our generalization of the three results we saw earlier, and this can apply to other kinds of generic hyperquivers. Okay, so maybe if someone has questions about the idea behind proving this result, you can ask, but I'm going to just skip over the proof. What I want to do is end this talk on some problems that you can think about. Actually, sorry, let's do a small example. Let's say we have this hyperquiver here. There's C3 on two vertices. T is a generic tensor, and those two edges will contract T in different ways. So it'll take two vectors x and y and contract them in the first and third component and in the second and third component, and we require that these are both scalar multiples of x. Okay, then we compute n for the singular vector variety. We find that it's 0, so we expect finitely many singular vectors, and we compute this polynomial that was shown in the theorem, and we get this expanded product. So we see that the coefficient of h1 squared, h2 squared is 15, so the theorem says that there are 15 distinct singular vector tuples. This is just a small example. Okay, yes, so back to some problems. So consider this hyperquiver here. So it's a cycle n length hyperquiver, and you have a generic tensor T which is placed on all of these hyperedges. And we remark that this hyperquiver representation is not generic according to our definition, because we have assigned the same tensor to edges in different partitions. And we note that its singular vectors are n-periodic orbits. So if you start with a vector here and you pass it along through all of the edges, you have to eventually come back to a scalar multiple of the vector you began with. But if we just pretended that this hyperquiver representation was generic, even though it isn't and our theorem doesn't apply, if we just pretended that it did, we would find that singular vector variety would have dimension 0 and degree m-1 to the n times d-1 over m-1 to the n-1. So that's what the theorem would predict. This is actually the correct answer. So this is proven in a complex dynamics paper by Fornés and Sibony in 1994. And notice in particular that if n equals 1, a cycle of length 1, this is just the Jordan hyperquiver, and this formula then recovers this Cartwright-Sternfels theorem. So what this n-cycle hyperquiver example suggests is that it should be possible to weaken the definition of a generic hyperquiver representation so that the theorem can apply in more cases. So the problem is to find what these weaker genericity conditions are. Another approach is to study the scheme defined by the equations of the singular vector variety. So we study the singular vector scheme, and a related question is there a Jordan canonical form for hyperquiver representations like there are for matrices and tensors? If you look at hyperquiver representations pictorially, they are like a network of tensors. So is there some connection with tensor networks? And recall that the singular vectors of a tensor are critical points of the best rank 1 approximation for a tensor. So can the same be said about the points of the singular vector variety? Is it connected to some best rank 1 problem? And lastly, is there a meaningful representation theory and moduli theory for hyperquiver representations like there is for quiver representations? So I'll leave this up. This is all I have to say, and thank you for listening. Yes? Yeah, that's a good question. Yes, sorry. Yes, the question was, there's a notion of path algebras for quivers, and representations of quivers are essentially like path algebra modules. Is there something like this for hyperquiver representations? I don't know. I haven't seen anything about hyperquiver representations in the literature. This is sort of related, but some people are looking at higher category analogs of quiver representations and higher category analogs of path algebras. So yeah, this is something people are studying. they're not hyperquivers, but they are some, yeah, generalization of quivers. But yeah, it's a very new topic and very little is known about it, and people are still arguing about how to define these objects.
Any other questions? There are no questions